So I was asked by several people to discuss the issue of importing the reference foil along with the standard. So before I start talking about Artemis, I want to take I think it'll take just a couple to explain how this works. So we're going to go back to the example that I showed you all yesterday. I'm going to import, so here's that iron oxyhydroxide, the first iron oxyhydroxide standard that I imported the other day. And so again, I need to select I0 over IT natural log, right? That's how we import the standard. And I see that I've got the right thing selected there. To import, okay, so if we go and look at the contents of this file, we see that there's the 0 column, the T column, and the R column, 0, T, and R. So I click the button that says Import Reference Channel, and it was somehow clever enough to pre-select IT and IR as the numerator and denominator. You would need to then choose the correct thing there also. And we can replot the reference to see if that's making sense. And I can't bring it to the top right now because this is grabbing focus. But that is, in fact, the iron foil that was in the reference position. And one button that deserves a little bit of commentary is this one here that says same element. There are some things for which it might be more convenient to use a different element as the reference if it's something unusual or, I don't know, possibly dangerous. You might find some other material that you can put in the reference channel that will have an edge in the data range. And so if you've done that, you need to tell it that that the reference is not the same element as the standard. Anyway, for most things this would be ticked on. I click OK. And all the stuff from before happens. But one more thing happens. A new entry gets put in the list. And so these are two things from the data file, the standard and the reference for the standard, and they're marked like that. So now I'm going to go and open the other two lepidocrocite samples. And it's remembered not only the columns up here, but it's remembered that you want to import the reference channel. So I click OK. And wait for it to plod through its thing. And now here we have all three data files imported with their reference channels. Now, so we have a frustrating thing going on the with this projector. It's a shame. This is not the best projector ever. And if any of you are following along on your screens, you'll have noticed that, or hopefully you'll notice that this box right here is the color in the background is not white but blue, and it really doesn't show up on the screen. So the fact that this box is blue is meaningful. It's an indicator, like a guide to the eye. It's something to draw your eye. It's a hint for how this whole reference thing works. So that box is blue for all of these data. All right, so what we can do now, let's do this experiment. Let's plot the lepidocrocite data with its reference. Plot those two together. And we see the sort of thing that we expect to see, a substantial shift to higher energy in the iron oxide compared to the iron metal. So that's what you expect to see from metal and oxide. So we can use the alignment tool, and the way we use it will be, the way I'm going to use it will be like this. I'm going to select the last reference, and then switch to the alignment tool. And I don't quite have the right thing plotted right now. It's using the data for 0, 0, 0 as the standard. And I want to go into that menu and select the reference for that one as the standard. And so now I'm plotting the derivatives of the two iron foils. I can, and as we saw yesterday, these data are actually already pretty well aligned. So when I do the auto alignment, it's going to come up with just a very small correction. But that's what it thinks the alignment needed to be. I'll do the same thing for the other one, auto align it. I could, of course, use the automation also, but this isn't a lot of data. All right, so now I'm going to go back to the main window and select all the references. And if I plot those all together, they've been very nicely aligned. So the way that this works is that each of those pairs is tied together. If we look at this value for the energy shift that the alignment algorithm came up for the reference, it was that number. And if we go look at its corresponding data, it's the same number. Now if I go back to the reference and I just by hand change this to a different number, so now it's 1.03, and I go look at the thing that it's the reference for, it's also 1.03. This is the relationship between data and its reference. When you change the energy shift to do an alignment for one, it drags the other one along. Right? So that's why we can line up the reference foils and have the data be properly lined up. So the one drags the other one along. That is what's being indicated by that blue color that we can't see up on the screen, and that's what it means for a sample to have a reference. Okay, so that wasn't supposed to be 1.0, it was supposed to be 0.03. So I'll change it back, and of course that one is also 0.03 because they're tied together. If you move one, the other one moves. Okay, so all of this was not particularly necessary. We could have done what I did yesterday and just aligned the lepidocrosite one to the other. But suppose that the next file I were to read in was this one right here, which is FES2, something we're about to become very familiar with. The structure of the file is the same, so it picked the same columns. It remembered that I wanted to import the reference channel. So I say OK. And there we have the pyrite data and its foil measurement. Let's plot the pyrite with the lepidocrosite. So now the question is, these are not the same material, but we want to plot them on the same absolute energy scale so that this energy shift is meaningful. If we have some instability in the monochromator, like I was talking about yesterday, the problem that we have at my beamline and at some other older beamlines, and to a lesser extent at newer beamlines, although as somebody, it was you with the up and down quick scan data, he was having the problem that there was a significant calibration problem on the up scan compared to the down scan that had to be just corrected after the fact that I presume, well, I'm not really certain how it's implemented at the beamline, but there was this problem, and it was off by tens of volts. So there are calibration problems that you have to worry about even on modern beamlines. Okay, so these two things are different. They have to be put on the same absolute energy grid. That is the purpose of the gold foil. If we align, if we align the references are the same thing. They're both gold foils. So we align these. This shift of 0.1 volts puts this sample on the same absolute energy grid as this sample, so that now when we plot these two things together, because their reference foils have been aligned, this energy shift is physically meaningful and interpretable and defensible. And that's how reference foils are done in Athena. So is that clear to the folks who were asking about that? All right, that was that. So now we're about to dive into the next big thing. So at this point, I've sort of talked about all the data processing that I have to talk about. There are probably more details and stuff will come up, but what's on the agenda now and what I'm about to start to go into is the other program, the Artemis program, which is the thing that you use to analyze the extended EXAFS data. So now we're going to get into using that program. It's going to be another program that we have to figure out how to use. And we're also going to start looking at theory and how the theory relates to the data. So by lunchtime, we're not going to have gotten very far into using Artemis because there are some complications, but we'll see how it goes. We'll see. Okay. Close. No. Now, in the data examples that I gave you, you got, so I've already poked around in here a little bit. What you have on your computers are this .inp file and this data file, and we're going to use the data file right now. So to get started in Artemis, we first have to have processed our data in Athena. So to get started on this, I'm going to go import that mu of E data. And this is just FES2. I took this off of, so Matt Newbill has a small data library that he keeps on his server. If you go to exafs.org and click on the databases page, you'll find a link to Matt's standards database. And it's not very big, but it's got some useful stuff on it. And that's where this came from. And these data have already been processed from raw data to mu of E. So what I want to do here is just click on the XMU column, and those are already mu of E data. There we go. So these are already mu of E data. All I need to do is click on that button and then click OK, and the data will be imported in. So OK. And as you can see, normalization happens, background removal happens, we have chi of k, we have chi of r. It turns out these data are quite reasonably well processed just by all of the defaults, so I'm not really going to play around with it very much, except for one thing. I do want to show you one thing, because I was asked about this a couple times yesterday. So I want to point out that this is an example of data for which you do need to look at your pre-edge, your normalization parameters, because for some reason these data have a funny thing right here, right at the beginning. And so it's hard to see, but the lower bound of the pre-edge range, the little orange circle, is right there. So by happy coincidence in this case, the default values for the pre-edge range were chosen well to fit in this flat part. But had this number not been chosen well, had it been somewhere out here, you would have had a slightly incorrect pre-edge range. And so this is an example of data for which you actually do need to, check and make sure that things are done correctly. I'm going to save this into a project file because the workflow for doing the extended EXAFS data analysis is you process your data in Athena, save a project file, and we're going to import the project file into Artemis. So I'm going to save it to fes2.prj, a good name. Overwrite, yes. And we're done with Athena now, so I'm just going to close Athena. And click on Artemis, which is this one right here. Wait a second while it loads itself up. So when Artemis starts up, two windows appear. This is the one at the top of the screen that goes across the whole top of the screen is sort of the master control panel, and it's sort of everything starts from up here. This vertical window, which is sort of and started off a little bit off screen, so I'll bring the whole thing up. This is sort of a low resolution monitor, so this Artemis works great on a really big screen, and there's sort of a lot of windows that you have to dig through on a smaller screen like this, but we'll make do. This is the connection to the server has been lost. Ruh-roh. I'm going to keep on talking. So this window has all of the stuff that we're going to need to make plots and visualize the data. You'll see how that works when we get there. For the moment, I'm just going to slide this back down and leave it there for a moment. So we need to import some data. So this part of the screen is where data gets imported into. I'll just, instead of talking about it, I'll just show you what happens. I click the Add button and go find that Athena project file that I just saved. So there's that Athena project file. And it opens up with the standard project file dialog. Had this, so this was a pretty uninteresting Athena project file. It had just one bit of data in it. If it was something with lots of data, then there would be a whole list. And you would select the one from the list that you want to import. The one that you have selected gets plotted so you can look at it and make sure that it's actually the data you want to import, which in this case it is. So I click Import Selected Data, and this window appears. So this window has two sides. On this side is unable to reconnect to the session. Please verify that you're connected to the internet. Well, I'm going to do that. See if I really am connected to the internet. The answer to that is yes. Session. Okay. And I'll start recording, I guess. And now I'm going to carry on, and hopefully that works. All right. Technology in action. All right. So on the one side, you have all of the parameters that are going to be used to describe the data. And it turns out that these values for the Fourier transform range and Rmin and Rmax, all of these things were all imported from the Athena project file. So if you had worked on your data to the point where you had the Fourier transform range and other things just so, they get preserved. That is, they get read from the Athena project file into here. What's going to happen over here is all of the stuff associated with the theory. And again, I'm just going to start showing you how this works, and hopefully it'll all start to come together and make sense in a little while. So FES2 is a crystalline material. It's relatively simple. It's a cubic crystal, but it has some interesting internal structure. It's basically iron surrounded by sulfur, and we'll see how that works. So because this is a crystalline material, and the data is collected on something that was probably like a powder spread on tape or something like that, I'm going to do the theft calculation on the crystalline material, and then we'll start to see how to think about the two things together. So the next step at this point is to import crystal data. There's a whole bunch of ways to do this. Clicking that place right there does the same thing as clicking this right here. There's a bunch of ways to get started on this. What we're supposed to do, what it's looking for, is that you will navigate in the file selection dialog to a file that contains crystal input data. And this could be the sort of simple description of crystallography data that I've been using in my software for some years. You can also import CIF files if you have access to a database of CIF files. There's a bunch of things that can be read in at this point. Here is some crystal data, and now another window has opened up. I should point out that when I added the data, a button showed up here that contains the data, and that does some screen management. If I wanted to hide the data, that makes the data go away, and that makes the data come back. Similarly, that makes the theory window go away, and that makes the theory window come back. Now, what's been imported from that little file that had crystal data in it is the results of a crystallography refinement. So we have a space group, and hopefully at least some of you in the room are at least passingly familiar with how this crystallography stuff works. There's these weird symbols that describe the internal symmetries of a crystal. The other information that you need are the lattice parameters. So this is a cubic space group, and the unit cell of this cubic space group has all its lattice, well, it's cubic, so all of its lattice constants are the same, and they're all 5.4 angstroms. You then, inside the unit cell, the crystallographic unit cell, you have some iron atoms and some sulfur atoms, and it looks like it disconnected again. So you have some iron atoms and some sulfur atoms, and the unit cell gets populated with iron and sulfur atoms according to the symmetries that are encoded in this space group symbol. So I mean, all that crystallography stuff about how you make a unit cell of a crystal, that's stuff that the software knows how to do. So what's about to happen is the software is going to interpret all of this crystallographic data, and it's going to fill up an entire unit cell. It's then going to stack up a bunch of unit cells in all directions to make a big cluster of atoms centered around one of the iron atoms. So again, instead of talking about it, I'll just show you. So the crystallography stuff happened, and it made a big list of atomic coordinates. And this is the kind of information that's needed for the theory. The theory needs to know a big list of atomic coordinates. So we have an iron atom at the origin, and surrounding it are a bunch of sulfur atoms at 2.3 angstroms, then a bunch more sulfur atoms at 3.4 angstroms, a couple more at 3.6, then there's a whole bunch of iron atoms. The data that PhEF is looking for are the Cartesian coordinates of all of these atoms. So this is much the same kind of information that you would need if you wanted to have a crystal viewing program make a ball and stick figure of what iron sulfide looked like. It's much the same, except it's shifted so that, in this case, it's been shifted so that there's an iron atom at the origin, and everything is then organized radially around the iron atom. So PhEF actually needs 4 numbers to identify each atom. There's an X, Y, and Z Cartesian coordinates, but then there's also a number in this column, which is 0, 1, or 2. I'll scroll down so you can see some examples of 1. So these iron atoms down here are all 1. And the index just identifies for PhEF what kind of atom is to be found at that position in space. So the input to PhEF is X, Y, Z, and potential index. With those 4 numbers, you can build a cluster of atoms surrounding an iron atom. And that's what PhEF wants. So I haven't done any theory yet. I've just converted crystallography data into an ordered list of atomic coordinates. I'm now ready to go run PhEF and generate the theory. And this takes a couple seconds, this part of the program. So we'll be patient. And now what it's come up with is a big list of scattering paths that are ordered in terms of increasing path length. So the first three examples are pretty easy to understand. So if we go back and look at the list of atomic coordinates, there were 6 sulfur atoms at one distance, 6 at another distance, and 2 more at that third distance. And we see that we have 3 single scattering paths. That is the kind of path that leaves the iron and scatters just off of the sulfur atom and then closes the loop. And there's 6 of them at the first distance, 6 of them at the second distance, and 2 of them at this other distance. There's then something else, and then there's another single scattering path. So you'll notice that all of the single scattering paths and a few other things are colored in green, and that's to draw your eye that those ones are probably quite important. So this 5th item in the list is the single scattering path to the iron. And then there's other stuff. So there's a whole bunch of stuff that Pfeff has calculated and made available to you to go on and do the data analysis. So what I'm going to do now is select a whole bunch of these paths by click, and now I'm going to hold down, the desktop beamer thing has disconnected from the network twice while I've been standing here, so we'll let Brian do his magic for a second. Oh, I'm going to, yes?
Just in the meantime, what does Pfeff relate to? Why is it called Pfeff?
Oh, I'll answer that question in about 5 minutes.
Okay.
Yeah, I haven't gotten to the point in the lecture where the name starts making sense, but I'll be there soon. And I'm going to use the time while Brian is doing his thing to write down the EXAFS equation on the board, because we're going to need that shortly. Are we good to go now?
We are, yes.
All right.
We'll stay up though.
Okay, so yeah, I'm going to need that shortly, so. All right, so, okay, the next thing I'm going to do is just the mechanics of using the program. Bear with me for a minute. Things will start to make good shortly. Okay, so I'm going to click on the first one, and then go down and shift-click. Nope. Isn't it shift-click? Yes, there we go. Shift-click on the one that's the 11th one, the one that's 0010. And that selects that whole first block of paths. I'm then going to click, drag, and drop them over here. And now what's happened is all those first several paths have now been associated with this data. Associated with the data. It'll all make sense in a second. Let's put this window away and start talking about how plotting works in Artemis. So plotting is a hair more complicated, perhaps, in Artemis than in Athena, but this complication gives you all the flexibility that you need to make all kinds of interesting plots of the data and the paths. So simply put, everything that's in this list down here will be plotted when you click these 3 buttons, and there's stuff all in this region that determines exactly how the plot gets made. So right now, if I click the R button, the data gets plotted in R, and if I click the K button, the data gets plotted in K because the data is the only thing in this list. Yeah, that's not working well. So what I want to do now is start examining how these different paths relate to the data. So what I'm going to do to get started on that is select the first path in the list, S1, and then I'm going to click on this little button right here, which serves the purpose of transferring the path, this path, over into the plot list. Now, when I click one of these buttons up here, everything in the path list, in the plot list, will get plotted. So now I'm going to plot in R, and we see that the first shell, the scattering from the nearest neighbor sulfur atom, contributes to the EXAFS in the Fourier transform in this region. So what's being plotted here is the Fourier transform of the data and the Fourier transform of Pfeff's calculation of the EXAFS contributed by the scattering from the nearest neighbor sulfur atom. And it Fourier transforms and has a peak in the same place as the first peak in the data. So the distance to the first shell has something to do with the position of this peak in the data. Now, the green line, the plot of the path, is much, much bigger than the data, and that's because in the EXAFS equation, which we saw briefly yesterday, in the EXAFS equation, I haven't done anything to evaluate S0 squared or sigma squared. Sigma squared is currently 0, and S0 squared is currently 1. When we actually do the fit, part of what we'll do in the fit is adjust these numbers so that the green line looks like the first part of the blue line. So what I'm trying to do is draw your attention away from the fact that it's much, much taller and draw your attention toward the fact that the peak is in the same position as the first peak. So it seems as though the Fourier components in the data underneath this peak are in large part, or perhaps entirely, explained by the contribution from the first shell scattering. Okay. I'm going to turn off the plot, untick this button just so there are fewer things plotted in the window. Okay, now I'm going to untick that so that it now won't get plotted. Okay? And I want to go and put in the next 3 single scattering paths. So I did that by clicking on each one successively and then clicking on that button. That moved each of those paths down into this list over here. So now when I click the button, the data is going to be plotted along with the contribution from the second shell sulfur, the third shell sulfur, and the nearest iron scatterer. And let's see what that looks like. So again, it's a little bit surprising to look at because all of the peaks are enormously larger than the data. But again, that just has to do with the fact that I haven't considered any values for sigma squared at all. So I haven't included any disorder yet. It's just the raw theory calculation. Without any disorder, without any consideration of S0 squared, we're going to get there. What I want to draw your attention towards is the fact that the second shell sulfur is peaked at about the same place as this peak right here, and that the iron peak is peaked at about the same place as this peak. So to some extent, this peak right here has something to do with the second coordination shell, and this peak right here has something to do with the iron coordination shell. But it's not quite that simple. It's more complicated than just pointing at a peak and saying that peak is some atom. And we can already see why it's more complicated than that. Because we have this whole other scatterer here, those 2 sulfur atoms that were at about 3.6 or something like that. Those two scatterers contribute where this green thing is. And you'll notice that there's sort of interesting relationships between the red, the green, and the blue. The green overlaps substantially with the red, and the green overlaps substantially with the purple. And in fact, the red and the purple themselves overlap substantially. So the point I'm driving at here is that, well, in short, the Fourier transform of chi of k is not a radial distribution function. You can't just point at a peak and say, that peak is an atom, and this peak is...
Please. The fire alarms are about to be tested. No action is to be taken.
Okay.
Your attention, please. The fire alarms are about to be tested. No action is to be taken.
So how imminent is it?
No.
Now, so I should wait?
Well, it only lasts about 15 seconds.
There we go. Okay, so no action is to be taken, all right?
May I have your attention, please? A fire has been reported. Please leave the building immediately by the nearest exit. May I have your attention, please? A fire has been reported. Please leave the building immediately by the nearest exit. May I have your attention, please? A fire has been reported. Please leave the building immediately by the nearest exit.
Are we done yet?
Yeah,
We're done, all right.
Here it's over, Bruce.
Your attention, please. The fire alarm test is now complete. Please obey all alarms.
Okay. Everybody clear? We abide all further alarms,
Your
okay?
attention, please. The fire alarm test is now complete. Please obey all alarms.
Okay. So, the point I was making before all that was that the blue line is not a radial distribution function. It's the Fourier transform of chi of k. We are going to analyze the Fourier transform of chi of k to extract information that will tell us about the radial distribution of atoms around the absorber. But chi of k is itself not a radial distribution function, and you can see that in part already because, well, you can't just point to a peak and say it has to do with one thing. The details of how these two peaks arise has something to do with the details about how, well, at the very least, how these three paths are going to add together. Because they all three of them contribute spectral weight all throughout this range. So what we've seen so far is that the first path contributes the preponderance of the spectral weight to this peak. But this blob of peaks right here is apparently going to be some kind of complicated combination of several things. Well, it really could be quite a bit more complicated than that. We have some more things to look at. So I'm going to first clear this list, and then I'm going to put the data back in the list. And now what I want to do is consider these. So we also, on top of all of our single scattering paths, which are these ones, the one that's highlighted right now, and this one, and we know those are all single scattering paths because they only have one atom listed. These other ones are various kinds of multiple scattering paths. So these two that say S1, S1 are two different ways to have the photoelectron leave the absorber, scatter off of a sulfur atom in the first coordination shell, scatter off of a different sulfur atom in the first coordination shell, and then close the loop. This one down here is a scattering path that scatters first off of a sulfur atom in the first coordination shell, then off of a sulfur atom in the second coordination shell, and closes the loop. So this one, this one, this one, and those two are all double scattering paths that make some kind of triangle in the material. This last one down here is a triple scattering path that makes some other shape, something that bounces 3 times. So the first thing I want to do is, what I want to do is examine in this sort of approximate way how each of these things are going to contribute. And so we'll do them in groups of 3. We'll do the first 3 and then the second 3. So what we did before was click on each of them and click this button and click, 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 click. There's a bit of automation. We can mark some of the paths and then go in the Actions menu and say Transfer Marked. And that says to transfer them over to the plotting list. So now we'll be able to plot the data and those 3 multiple scattering paths. So let's see what that looks like. I think I missed the button. There we go. I somehow missed the button. Okay, so these multiple scattering paths, well, 2 of them, these 2 that are triangles bouncing in and around the first shell, are pretty small, pretty broad, diffuse things. This thing that goes from sulfur atom in the first shell to the second shell, it's quite a bit bigger, and all of them contribute spectral weight all throughout this region where those 3 single scattering paths contributed spectral weight. But of course, I still haven't applied any value for sigma squared in the fit. So when we actually go to evaluate things, they'll be somewhat smaller than they are right now. But this shows us how those multiple scattering paths relate to the data. Very well. Let's untick those there, untick those there, and tick the next 3. And I'm going to transfer those over. And now we're going to make a plot of the data and those 3 multiple scattering paths. And this will be something kind of interesting. So 2 of them are really tiny. These 2 are even smaller than those 2 there. These are quite small contributions to the data. However, there's this one multiple scattering path, the one that first hits sulfur in the first coordination shell, then hits the iron atom, and then closes the loop. It appears to have really quite a substantial contribution to the EXAFS. So here's an example, it would seem, of a multiple scattering path that we simply can't ignore. It would seem that we're not really going to be able to explain the whole shape of this thing without properly considering at least some of the multiple scattering paths. So that tells us, well, I guess there's 3 things that I want to highlight at this point. Thing 1 is that, again, the blue line is not a radial distribution function because, look, there are big multiple scattering paths that contribute. If it were something like a radial distribution function, then we would only see the contributions from the single scattering paths, and that's not the case. There are clearly important multiple scattering paths. The Fourier transform of chi of k is not a radial distribution function. And in fact, I regularly send papers back to authors who use the phrase radial distribution function in a manuscript. I do not allow that to be published when I'm the referee. So if you say that and send it back, you might have had me as a referee. So just don't say that. Do it right from the beginning. Okay, that was thing 1. Thing 2, I've already forgotten what my list of 3 things to talk about were. So it's not a radial distribution function. Oh, thing 2. Thing 2 is that we haven't done any work yet, right? We haven't actually talked about how to do a fit, and we certainly haven't fit any data. All we've done so far is plot data and plot the contributions from paths. This is how I always start a new data analysis project. For me, it's too complicated to I can't wrap my brain around new data and new theory and stuff I've never looked at before. I have to break it down into pieces. And for me, this is the best way to do it, because I get to actually see how each part of the theft calculation compares to the data, and compare them in very equal terms. And we've learned a lot just by doing this. We have learned, for example, let me clear this again and set up the plot I want to look at right now, which is this. We have learned that pretty much the only thing in our theft calculation that contributes significant spectral weight to the first peak is the first scattering path. That's useful information. We haven't done a fit, but we already know something about our material. And we've also learned that there's a whole bunch of things that contribute spectral weight underneath this peak. At the very least, I think we are going to need to consider these single scattering paths and these two multiple scattering paths. At the very least, we're going to have to consider those. So understanding this blob here is going to somehow require figuring out how to include at least these 5 things into the fit. So again, I mean, we're going to need to talk about how to actually do that and how to set up the fit and all the mechanics of that and all the science of that. But this is useful information. We could do a first shell fit only considering, we could do a fit to the first peak only considering the first shell, but all the rest of this stuff somehow combines up to be this peak. Now, I should point out also that it's not, the situation isn't quite so simple as sigma squared not yet being evaluated. There's some kind of phase relationship here. So if we look at the real part of the Fourier transform, we see that there's some kind of complicated phase relationship between all of these things. So it's not just that those magnitudes were all going to add up with the appropriate sigma squareds and S0 squareds, but all of these oscillatory functions are somehow going to add up, parameterized correctly, are going to somehow add up to be the blue spectrum. So this is really what the problem is that we need to get all of these wiggly things to add up. And like I said, we're going to have to include even stuff like this one right here, which is a multiple scattering path. All right. So now it's time to actually start doing some fitting. What hour are we supposed to stop?
Anywhere, quarter past.
On pause, but we can.
Whenever any suitable moment.
Okay,
Yeah.
so how about about 5 more minutes?
Yeah, that's
and
fine.
I'll get to a good stopping
5-10
point.
minutes done.
Okay, so to do the first shell analysis, it's pretty simple. What we want to do is, well, first of all, put the data back, and plot in magnitude. We want to do the fit just over the first shell, so we're going to restrict the fitting range to be from here to here. So the way we do that is, we'll say start the fit about there. That's 1.3. So R min will be 1.3. And we'll do R max at this cusp down here, which is at about 2.3. So here we'll say 2.3. If I hit the carriage return button right now, I get an interesting little snippet of information down at the bottom of the screen. It uses these values, the Fourier transform range and the fitting range, to tell me an approximation of the amount of information in the spectrum. So what this says is that in the best day, the best of possible situations, we might be able to measure 6 parameters out of the data Fourier transformed over this range and fitted in this range, just the first shell. Now, we're only going to need 4 parameters to do this. So so that set the Fourier transform range, or that set the fitting range to be like that. Now the other thing we have to do is include just the first path. So there's a number of ways to do this. We could click on each one that's not in the first path and unclick the button that says Include Path. That gives you this little visual clue that it's been taken out of the fit. That means that this path is not going to be used to evaluate the fit, but it's still here and available to you should you want to come back to it later. So when we go and do the fit to more of the data, we will include some of these other paths. Right now I want to, well essentially I want to go click, 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 and so on, but that's a little bit tedious. So instead I'm going to click on the first path, go to the Path menu, oops, no, go to the Marks menu, and say Mark After Current, and that put on all the tick marks for everything except the one that I was on. I then go to the Actions menu and say Exclude Marked, and now I've taken all of these out of the fit. So we're almost there. We've set the fitting range. We've included just the contribution from the first neighbor. Now we need to somehow parameterize the fit. I should have stopped when I asked you. Now I have trouble seeing this finishing in 5 minutes. So I actually think we should take a break now and come back to this after lunch. So after lunch I'll start to talk about how to do the parameters of the fit so that we can be ready to hit the big button up here and actually do some data analysis.
Said we're not ready.
Oh, lunch isn't ready.
Yes.
Oh, so I should keep talking.
Yeah, 10 more minutes.
10 more minutes. Okay. All right. So now it's time to look at the EXAFS equation for a while. So R equals R naught plus delta R. Okay. So the way the fitting works is like this. This is the EXAFS equation. So the contribution from each path has to be evaluated. We somehow evaluate this equation for every path that's included in the fit, and then add up all the paths that are included in the fit, and compare that to the data. So to evaluate the EXAFS equation, we have to come up with values for every term in the EXAFS equation. This is the oscillatory part, the part that makes it wiggle. This is the disorder part, the part that damps the signal and decreases the size of those peaks. N is the coordination number, or for a multiple scattering path, the degeneracy of the multiple scattering path. For the case of a single scattering path, it's the coordination number. So we have 6 sulfur atoms in the first coordination shell, so N is 6. This is a crystalline material. We know that N is 6. And S0 squared is this so-called passive electron amplitude reduction factor or some such thing. It basically is there's a small effect in the data where the theory calculates its theory with all of the other electrons in the system in the state that they were before the photoelectron gets created. But in truth, when the photoelectron gets created, all of the other electrons relax a little bit because the screening has changed, because you've taken an electron out of the system. So there's a slight change to the electronic state of the entire system, which results in this term in the EXAFS equation being somewhat less than 1. So S0 squared is a term that in practice comes out to be something between 0.7 and 1, and just quantifies the effect of the relaxation of all the other electrons around the core hole. So somehow we're going to have to evaluate that number. F of k is the scattering amplitude. So photoelectron goes out, scatters off of a neighbor. The amplitude of scattering as a function of k is this term. This is something that we get from Pfeff. So Pfeff gives us F of k. Then we have the sinusoidal term. It oscillates as 2kr, where r is the distance between the absorber and the scatterer for a single scattering path, or for a multiple scattering path, 2r is the total path length of a multiple scattering path. So this r is something about the distance that the photoelectron travels. Delta of k is a phase shift due to the scattering off of the scattering atom. So photoelectron goes out, it propagates out, and it suffers a phase shift when it scatters off of the surrounding atoms. Delta of k is another thing that is calculated by Pfeff. And then there's the damping term, the sort of Debye-Waller factor-like term. So R is calculated at some value in Pfeff. We gave Pfeff input data, right? That big list of atomic coordinates. So when Pfeff was calculated, for every path, there was an R naught value, which was the distance of that path in the calculation. But one of the parameters of the fit, one of the things we want to do in the fit is allow some freedom for R to adjust in the fit so that we can actually measure what the distances are in our actual sample. So the R that goes in this equation is R naught plus some parameter delta R, which is something we're somehow going to determine from the fit. So, in the fit, we measure delta R, and we need to somehow determine sigma squared also. That's something that will come out of the fit. S0 squared, possibly n, although as we'll talk about in a second, n is not an unknown in this fit. N is 6 in this example. But in general, n is something that has to be evaluated. And there's another thing that I haven't written down that's an energy shift, that a shift to the 0 of k, right? Where k equals 0 might need a shift. And why do you need a shift in the energy? Well, in Athena, you picked some value for E0. That set the 0 of k. In the theory, it picked some value of E0 and set the 0 of k, but they're not necessarily the same choice. So we need a parameter in every fit to line up the energy grid in the theory with the energy grid in the data so that the rest of the parameters can be determined correctly. So you will find that we always have a delta E naught that affects the evaluation of k everywhere it appears in the EXAFS equation. So the problem in front of us is to use Pfeff to supply us with these numbers and somehow extract these numbers from the data. So for every path that we include in the fit, we need to evaluate this equation, which means somehow determining these 5 numbers. That's the problem in front of us. Right now, the fit is relatively simple. It's a single scattering, a single scattering path, one single scattering path, representing the contribution from the near neighbor sulfur atom that we are going to use to describe the Fourier components underneath that first peak in the data. The way the program works is like this. And for those of you coming to this for the first time, what I'm about to show you is going to seem slightly crazy and vastly overcomplicated. You're going to have to bear with me. It's not going to, the reason for doing what I'm about to do is not going to become clear until after lunch. So for now, you're going to have to just sit there and think, wow, that's crazy. Why is it done that way? And shrug and keep up with me. This is how it works. So I am going to define, what's going on here? Okay, I am going to define a word to represent the S0 squared parameter, and I'm just going to call it amp for amplitude. I'm going to define a word to represent the E0 shift, and I call it E naught. I'm going to define a third word that is the delta R in the second line. And I'm going to define a word that is that represents the sigma squared at the end of the first line. Now, it's not sufficient to just write them down here, and this is the crazy part. The crazy part is that I have to open up this window up here that says GDS, and I have to guess an amplitude parameter and give it a starting value, the starting value I will give it is 1. Same thing I need to do. I need to guess an E naught, and I will guess it to be 0. And so on. That I will also guess to be 0. And the sigma squared parameter I'm going to guess to be something slightly larger than 0. So what I've done is I've defined 4 parameters that are going to be floated in the fit, and those 4 parameters are going to be used to evaluate S0 squared, delta E naught, delta R, and sigma squared. And these boxes correspond to the green things in the EXAFS equation. So I've defined 4 parameters, I've used them here, and those things are used to evaluate the EXAFS equation. So, it turns out I'm now ready to hit the big green fit button, and so I'm just going to go, so, E naught. Yeah. Oh, I know what the problem there is. I did not hit carriage return to finish this. There. Now I've defined it. You have to actually hit carriage return to get it to take. Or not. Oh, you know what it's telling me? Oh, I see what the problem is. I put in a typo. So Artemis has a spell checker. I spelled it E-N-O-T. E-N-O-T there. And that's actually an M, not an N. So I just typed it wrong. And it was telling me that I typed it wrong. E-N-O-T. Okay, now I click the fit button and a fit happens. Let's look at the plot. So here's a cool thing. So here's the result of the fit, and it's plotted in the magnitude of chi of r and the real part of chi of r. Just because it's useful to look at both. I find it's useful to look at both. So this is the default after a plot fit, is to look at the magnitude and the real part. And visually, it appears to be a good fit. We look at the log file, and we see what our 4 parameters evaluated to. So S0 squared came out to be a little bit smaller than I just suggested it should be. So that's something we're going to have to think about as we go on for the rest of the afternoon. It's a bit smaller than 0.7, and perhaps it shouldn't be quite that small. E naught is a few volts with an uncertainty of a volt. That's a reasonable sort of number. That doesn't make me unhappy. Delta R is a small number with a larger error bar. So basically our delta R is consistent with 0, which says that the iron-sulfur distance that was used in the crystallography data is consistent with our data. We have a delta R consistent with 0. That's a perfectly reasonable result. And a sigma squared of about 0.003 is the sort of size of sigma squared that we typically see in EXAFS data analysis. So except for a rather small amplitude, a rather small S0 squared, all of our parameters are pretty reasonable. The fit looks pretty good. We assumed that n equals 6 was the right number, which since it's a crystal is probably pretty reasonable. And there's our analysis of the first coordination shell. And now I think we'll stop and take a break. And well, I guess if there are any pressing questions, I'll answer them. I would assume that things are still pretty fuzzy and unclear. There's a lot more to talk about. But if there are any questions before we go to lunch, fire. Everyone will wait until after lunch. Okay. Fortified, then you can come back for more EXAFS analysis. All righty.